record.
Oh, record. What?
Okay.
Yeah, you're good. Okay, so today is our last lecture on electromagnetism, actually. So our next two lectures are on thermodynamics. This lecture we're talking about inductors. So first we're going to do our review quiz of lecture 6. Here's the worksheet for today if you haven't picked it up already. And then we'll do our lecture and problem solving in the lecture. And then after that, we'll be just making our cars. I got our magnetic wire. It's down in there. It turns out it's the same gauge as that stuff that we found last week in the circuits lab. So I don't know if it works better than that motor wire. I would imagine it would probably work similar, but you're welcome to try it out. And so next week is your race day. So you can spend, after lecture, you can just spend that time finishing up your vehicle and getting ready for next week. I'm probably going to bug out of here because my daughter's sick. So yeah, I had to drop her off at school and she wasn't too thrilled about that today. Okay, so let's review things from last week. Two positive point charges move side by side in the same direction with the same velocity. What is the direction of the magnetic force that the upper point charge exerts on the lower one? And my hint is this is just like two current-carrying wires. All right, who's ready to vote? Okay, most people. Who thinks the answer is A? 1, 2, 3, 4, 5, 6. Who thinks the answer is B? 1 vote? Okay. Who thinks the answer is C? Thinks the answer is D? 1 vote. Who thinks the answer is E?
Because I'm not sure.
Okay, not sure. Okay, all right. So a smattering of votes throughout, but the most votes went for A. So why did you guys who chose A choose A? Chris?
The modified right-hand rule, I suppose, with kind of the thumb in the direction of the velocity of the charge of the current, and then the fingers curl around, and then that would make the magnetic field, I guess, for the bottom one, for the top one, then the magnetic field is going to be pointing into the screen, which would then make the force upward.
Using the other right-hand rule?
Yeah, using the other right-hand rule, so it would pull that towards it.
Okay. Did anyone else use Chris's method to figure out their answer for A? Did someone, you use that method? Mm-hmm. Okay. Did anyone use another approach to get to the same answer? Jordan?
I took the good notes approach.
The good notes approach.
I wrote down that parallel currents track wires. Yeah.
All right. I like that. Did anyone else use that approach where they remembered that parallel current carrying wires attract? Do you just?
Yeah, I had a question. Sorry.
Yeah.
I thought you were going to ask another question, but so since these are positive point charges and they're moving in this direction, wouldn't the current be moving in the opposite direction? Well, I mean, it would still be the same. The answer would still be the same. But I'm just trying to think about it because I was doing current this way, but.
Well, when we use our right-hand rule involving current, I mean, this is a side point, but if we use our right-hand rule using current, we're using conventional current, and conventional current would be the direction of positive charges.
I'll have to remember that.
Yeah. Okay, so that covers why people chose A. There was no other answer where we had more than one person choose, but is anyone confident in another answer that they want to defend? Yeah, Nolan?
I think they will repel from each other because they are both positive charges moving at the same velocity in the same direction.
So in reference to the electric force?
Yes.
Okay. So the
Also,
electric
I
force...
remember there was a problem on the homework where you had to find whether they attracted or repelled. And from our reference sheet, I believe it actually said, okay, forces between parallel wires. Okay, it says there's, they repel each other because the currents are in opposite directions. Okay, maybe I'm wrong.
Well, you're not wrong that the electric force would be repelling, but the question asked about the magnetic force. So the net effect may be that they don't actually pull towards each other. It could be that there's a balance between the electric and the magnetic force. So the magnetic force is separate from the electric force. But you're correct that the electric force would cause them to repel. Anybody else want to add a argument for one of the other answers? No? Okay. Thomas?
Question.
Mm-hmm.
Can you explain how the right-hand rule works with current? I don't understand that.
Okay, so we've got two equations for the right-hand rule. Are you talking about the complicated right-hand rule?
Just whatever we're using to solve this problem, where whichever finger it is points at current, and we figure out which way the force is going.
Okay, there's two right-hand rules that are used for this one.
Oh, okay.
So for whether it's two current-carrying wires with current flowing parallel, or in this case where we've got two positive charges that are moving in the same direction. So you asked about current, so I'll do the current-carrying wires first, but the argument works the same for both. The simplified right-hand rule is just your thumb and your fingers. And you put your thumb in the direction of the current, and your fingers will curl around showing the direction of the magnetic field. And so for the top wire, it's got a magnetic field that curls around it like this. So we could draw that coming out of the board on the top of that wire. And it would be going into the board below that wire. And it would be into the board for all points below that wire. So you could draw that basically surrounding the second wire. It's feeling that magnetic field from the top wire pulling into the board. So that's the first right-hand rule. And then the second right-hand rule, we look at the bottom wire, and our equation that uses the complicated right-hand rule was IL cross B. And what we learned with the cross product is that matches up with our fingers with the complicated right-hand rule. So the first term is always our index finger. So this is the right-hand rule. That's my shorthand for right-hand rule. Your second term in the cross product is always your middle finger. And the result of the cross product is always your thumb. So, getting out my right-hand rule over here, my index finger points in the direction of the current. My middle finger points in the direction of the B field, which is into the board, and that shows that my thumb is now pointing upward. So that is the direction of the force on that bottom wire.
And that can rotate around too. The force is going outward.
The force is always upward. So the magnetic field creates a circular shape, but the force is straight up.
So even if there was an object below it, the force is still going up through the wire.
What do you mean an object below it? An object, a current carrying wire?
Well, you're saying that the force is going up, but that wire, it's symmetrical. So up on top and also down on the bottom, or is it also going up?
Every part of that wire is feeling an upward force. every single section of that wire, because the current is always going, for every single part of that wire, the current is all flowing that way. And every single part of that wire is feeling a B field into the board.
How does it know that that way is up when not down?
What do you mean? How does it know?
This, how would it just, I don't know, I can't explain it. Never mind.
If we had another current carrying wire up here, this current carrying wire, the current's going this way, the B field it feels is out of the board. And so for this wire up here, it would be feeling a force downward. So for this wire, it's creating a B field that causes a wire below it to be attracted upward and a wire above it to be attracted downward. The net effect is what Jordan summarized, that wires that have currents flowing in the same direction always attract each other. So it doesn't matter whether this is above or below, the net effect is the force is attractive. So did I help you understand a little better how to use your right-hand rule?
No, I'll have to ask you later, like during break or something.
Well, get out your hand.
I don't want to waste everyone else's time though.
Well, other people might have the same question.
Okay.
Tell me which finger is the current direction.
There isn't. According to that.
L is associated with the current.
Oh, okay. So the index finger.
Mm-hmm. And then the middle finger is?
The magnetic field.
Mm-hmm. And then your thumb?
Force.
The force, yep. And so you can practice this for every picture we do. This one, because they're charges, uses the other right-hand rule that we learned, Q, V cross B. The cross product, this applies to any cross product in the world. So this isn't just for magnetism, applies across the board in math land too. So the first term is your index finger, the second term is your middle finger, the result is your thumb. So first we use that simplified right-hand rule. So we put that in the direction that the charge is moving. That creates our B field that's curling around. So the B field down here would be into the board from that upper charge, B sub A. And then using our right-hand rule again, we put our index finger in the direction of V, our middle finger in direction of B, and then our thumb is pointing upward as our resultant force. So it's essentially the same result, but you've got two different force equations to get you there. Any other lingering questions? These are good questions. I mean, these are the things that you're going to be puzzling through on the test. This is all the concept stuff, not just how to solve problems, but this is sort of like before you even get started, this is the stuff you're going to use to set up a problem. Yeah, Kevin?
So if those were electrons, everything would be the same except the force would be pointing downward?
Yeah, good. Yeah, good job, Kevin. So yes, if this was an electron, we'd say our right-hand rule says this, but we know that it's actually downward. So, okay, so let's see what the answer is. The correct answer was A, so it is attractive. All right, next one. A long straight wire lies along the y-axis and carries current in the positive y direction. A positive point charge moves along the x-axis in the positive x direction. The magnetic force that the wire exerts on the point charge is in what direction? Okay, who's ready to vote? Some people. Do you guys need more time? I'll let you have more time. Okay, let's go ahead and vote. Who thinks the answer is A? B? 1 vote, 2 votes. C? 1, 2, 3, 4, 5, 6, 7. D? E? Okay, 7 for C was the most votes. So why did people choose C? Liz?
So I did the modified right-hand rule to find the magnetic, to find the B field. So you go up and then it's curling around. And so at that point, the B field is pointing into the board and the velocity is going in the positive X direction. So it would look like this. And so the force would be going in the positive Y direction.
Okay. So just like the last, what's that?
It's a positive charge, and so it would be going in the same direction.
Good, okay. Other people who chose C, is that how you went about it? Yeah? 2 people chose B. You guys want to defend B?
So I was looking at it as what the magnetic force of the wire is exerting on the point charge, not what the magnetic force of the point charge is exerting on anything else.
Mm-hmm.
So I used the right-hand rule, the modified right-hand rule, in the direction of the current, curling around, B field is into the board, and so then we switch over to the same technique we used for the previous problem, that the current is the index finger, B field into the board, then the force would be on the point charge would be in the negative X direction. That was my thinking.
Okay. So the first part of that was correct, where you use the modified right-hand rule. You put your thumb in the direction of the current, and then your fingers curl into the board on the right side where that charge is. So the B field over here is into the board. But when you're figuring out the force on a charged particle, we have to remember that we only get a magnetic force when we have a moving charge. So it's a property of the fact that that charge is moving in a B field that creates the force. And so that force, that magnetic force, is directly related to how fast that particle is moving. So when we use the modified right-hand rule, we have to base it on the charge itself, not on the wire. So that charge, it's like you could even ignore that the wire is there. Now we just have a charge that's in a B field. The B field is into the board, and so what would the force be on that charge? It's going to be related to the size of that charge and how fast it's moving. So that's why we're using this equation, and then we're going to use the properties of this charge, which its velocity is to the right, the B field it's feeling is into the board, and then the force from the right-hand rule says it's up. Since it's positive, then we can actually follow what the thumb is doing in this case. But I'm glad that that you made that mistake. I don't know if you are, but it's a good point of learning for everybody. So it illustrates sort of a potential area where we might make a mistake.
So basically, if we have a moving point charge, then we just use the direction of the current of the wire to figure out the B field, and then we just ignore it for the rest of the problem.
Exactly. Yeah. I don't want to single you out, Thomas, but I was just wondering how you did with this, if you had.
Oh, I don't know.
Okay, do you mind me putting you on the spot?
Okay.
Well, you want to just jump up here? Because learning this stuff really requires doing.
Okay.
Okay, so I want you to take your right hand, like this. Put your thumb in the direction of the current of this wire. And now curl your fingers. So which direction are they pointing for this charge?
Curl my fingers.
Like this. So they're curling around. They're making a big cylinder.
circle.
Yeah. So for this charge, it's feeling part of that circle, right? It's feeling the part that's going into the board. So that's the direction of what?
The force.
Close. What's the other option?
The field.
The field.
Okay.
Yeah. So that's the B field that this charge feels.
Okay.
So now we know the B field direction, we know the velocity direction. So using our complicated right-hand rule, how would you figure out the direction of the force? So index finger is what?
The current, and then
Not the current.
no.
What's this?
Oh, I was looking at the other one. So velocity this way,
Yep.
and then thumb is the force.
But what direction did we say the...
It's this one.
There you go.
Yeah.
There you
So
go.
then the force is upward.
Yeah.
Okay.
We figured it out. So it might feel a little shaky now, but doing this, it's like muscle memory when you're an athlete, right? You do something over and over again, like we're physics athletes now. You create that muscle memory. So what ideally, you want to do enough of these problems that when you read it, this is maybe like pie in the sky. You don't even have to put your hand out because you've done it so many times that muscle memory is already there and you know what your hand would do. So maybe that's your challenge, is to practice a lot of these problems to the point where you can just envision what your hand would be doing. Sort of like when you're in 4th grade and they say stop counting on your fingers. So I'm not saying don't use your right hand rule, but maybe that's your ultimate goal, is to have done so many of these problems that you don't even need to put your hand out because your hand remembers what it should do. I'm not there yet. Just full disclosure. Okay, moving on. Oh, let's just, what's that?
We found the answer was C.
Let's check. The answer was C, yes, correct. All right, 28.5. A long straight wire AB carries a 14 amp current. The rectangular loop has long edges parallel to AB and carries a clockwise 5 amp current. What is the direction of the net magnetic force that the straight wire exerts on the loop? All right, who's ready to vote? Just 3, 4, 5, 6. I'll give you guys more time. Would it help anyone if I told you that the numbers really don't matter? That helps? Okay. Those are useless information that they threw in here. Okay, why don't we go ahead and see what you guys think. Who thinks the answer is A? B? C? 1, 2, 3, 4, 5, 6, 7, 8, 9. D? E? 1? Was that misleading question? Oh, net magnetic force is 0. Okay. Was there 9 votes for C? So C. Okay. So why did most people choose C? Chris?
So going again back to that first problem, that for the top loop that's heading in the same direction as the current in AB, they would be attracted to each other. And although for the bottom half of the loop they would be repelling each other, my thinking is that the bottom wire would experience a smaller magnitude of that magnetic force, and therefore the overall force exerted on the wire would be less as well. So then the net magnetic force on the overall loop would be toward AB, because the loop carrying current in the same direction as current in the AB wire is closer.
Okay.
That was my thought process.
Okay. So you say because this one's closer, this vector is going to have to be bigger than this force?
Right, because
so this is going to give you a positive.
That the magnitude of the B field is going to be the permittivity constant times current over 2 pi r. And so as that r increases and we get further and further away from IAB, then the magnitude of the magnetic force created by that wire is going to decrease as we get further and further away. So the magnetic field at, I guess, the bottom half of the loop is going to be smaller than the magnetic force at the top of the loop. Or the, I'm sorry, not the magnetic force, the B field. It's going to be, that's where I'm at.
Yeah, okay. Anyone else who chose C use the same line of logic? Jeremy says yes, Jordan says yes, Nolan, Chris? Okay. You're the only one that voted? Do you want to defend E? Thought that was a good argument?
Yeah, I didn't think about it that way because I was doing it with my right hand rule all the way around. And so I thought that it would just cancel, but I didn't take into account the distance, so revert. Okay.
But, you know, I think the good part is you got, like, most of it there because you knew that there was going to be an upward force and a downward force. Yeah. So, okay, great. Any questions on that one? Not everybody voted, so did anyone have any lingering questions? I guess Chris did a really good job of explaining it. Let's see. The correct answer was C. All right. Next one. A wire consists of 2 straight sections with a semicircular section between them. If the current flows in the wire as shown, what is the direction of the magnetic field at point P due to the current? Okay, who's ready to vote? 1, 2, 3, 4, 5. I'll give you guys more time. Okay, anybody ready to vote now? A few more people. Okay, who thinks the answer is A, to the right, B, to the left, C out of the plane of the figure. D into the plane. Everybody, almost everybody. E. Okay, so why did most everybody choose D?
Using the other right-hand rule.